Welcome everyone to the ACEMS virtual public lecture series. My name's Matt Rowan and I'm a Chief Investigator with the Australian Research Centre for Excellence in Mathematical and Statistical Frontiers, which is ACEMS, and a Professor in Applied Mathematics at the School of Mathematical Sciences at the University of Adelaide. Before we get started, I'd like to acknowledge the traditional owners of the land on which we meet today and pay my respects to their elders past and present, and extend that respect to other Aboriginal and Torres Strait Islanders who are present and online today. I'd just like to mention that today's lecture is being recorded and will be made available at the ACEMS webpage, which you can easily find with Google or your favourite search engine. We're delighted today to welcome Professor Shane Henderson, presenting as part of the ACEMS virtual lecture series. Professor Henderson holds the Charles W. Lake Jr. Chair in Productivity in the School of Operations Research and Information Engineering at Cornell University. His research interests include discrete event simulation, simulation optimization, emergency services planning, and transportation. He's an Informs Fellow and a co-recipient of the Informs Wagner Prize for his work on bike sharing programs. He's won numerous teaching awards. He's the editor-in-chief of the open access journal Stochastic Systems and has served as the chair of the Informs Applied Probability Society. He's previously held positions in the Department of Industrial and Operations Engineering at the University of Michigan and the Department of Engineering Science at the University of Auckland. For fun, he likes climbing walls, biking, Harry Potter, and being a dad. So now, without further ado, Professor Henderson, welcome and thank you for joining us today.
Well, thank you, Matt. That's kind of you to do all that spiel for me at the start. I'm going to bring up a desktop here so I can show you a slide. Matt and everybody, thank you for coming. I appreciate especially everybody showing up for this talk today. We've all got a trillion things on our minds, and it's a bit overwhelming at times. So what I'd like to do is talk about something completely different. So before I do that, just one quick word. I'm not completely oblivious of the fact that we're living in strange times. I've been working pretty heavily on some modeling work for COVID-19 and a bunch of different research groups. And some of my friends in Australia with whom I'm working are I think, in the audience today. So really nice of them to come along. We're also doing some pretty heavy stuff here at Cornell to try to figure out how to keep our university open and running for our students. But I'm not going to talk about that. I'm going to talk about something quite different, just for a refreshing change. So again, thank you for coming and having listened to this. So this is work to do with maybe the modern forms of mobility, so bike sharing. And this is joint work with a bunch of very good people. In the interest of time, I'm actually not going to go too much into the details of all of these folks, but I will just say David Schmoys, that first person who's listed there, is somebody who deserves special mention. He was somebody that created this interaction with the company Citi Bike, which operates bike sharing program in New York, in the city in the US. And he created that interaction right from the word go. And then Citi Bike is a company that is owned by this company called Motivate, which is in the title here. So Motivate owns Citi Bike. And Motivate is now also owned by the company Lyft, the company that you probably know a little bit about with ride sharing. They're very similar to Uber. Anyway, so it's this weird tangled web of companies and so forth. But today I'm going to talk more about the science and the mathematics that goes underneath that. And I'm aiming this talk at folks who have some interest in mathematics, but are not, into the really curly stuff. By way of a sense of where this accent is coming from, I'm talking to you from the state of New York in the US, where we've previously had total nightmares with COVID, but things are looking a lot better now. But I'm actually originally from New Zealand, and so I'm actually pretty interested in how things are going down in New Zealand and Australia, so I've been keeping close tabs on my buds there. So anyway, that's by way of just getting going. Let's move on and talk about bike sharing, and this will be a nice break from COVID-19. Okay, so there's many different types of bike sharing out there in the world. And the one that I'm wanting to talk about is one that's based on stations. And so what is a station-based bike sharing system? So this is where you have a bunch of stations that look a little bit like this picture here. You've got a bunch of racks with bikes in them. And the racks, if you zoom in a little bit, they look like this. They're very heavy, but they're basically just this empty place into which you put your bike. And then you can stick these bikes into those racks. And then when you want to borrow a bike, you just go along and use your key, your key that's supplied to you because you're a member, to remove one of these bikes. You bike to where you want to go and you return the bike into the dock. And so here's somebody who's cruising along on his bike. I think he's either listening to music or looking at his cell phone or something, which is probably not recommended, especially in New York City, but it's all good. So this is the kind of system I'm talking about. So I'm not talking about those systems that you may have heard about in places where they have free form kind of models. So there's no fixed stations and you can just pick up and drop off bikes anywhere. That causes chaos in a large city like Melbourne or Sydney or here in New York City. So it's a station-based system. So the main operational challenge you encounter here is, as this unhappy looking lady on the right here seems to be indicating, imbalance. So what we see, it's pretty clear on the right, there's no bikes and she wants a bike. And on the left-hand side, there's somebody coming in to return a bike and there's actually no space for him to return his bike into the racks. And that's a problem. So that causes frustration with the system. And in fact, when we first started getting going with this, people started to, at Cornell, and also our friends in New York, started to learn that we were doing this work with Citi Bike. And so we became the target of their irritation when things weren't working the way they wanted. So we would get messages like this, right? So check out downtown between Reed and Park Place, west of Broadway, no docks, no one doing anything about it. Number of angry bikers. So I want you to focus on that number of angry bikers. That's actually going to be important going forward. That's the thing that we're trying to avoid. So what we're going to do is we're going to develop tools and analyses that help us to design the system in a better way so as to reduce the number of angry bikers. And that involves a combination of statistics and optimization and applied probability and all kinds of cool stuff. And I'm just going to try to give you a dusting or a taste of what that all involves. So what kind of data do we have available to us? Well, Motivate and Citi Bike are a pretty major operation now. Motivate operates most of the very large bike sharing systems in the US. And you're probably used to thinking about a lot of Americans as driving enormous SUVs, maybe smoking cigars while they do it and everything. But there actually are quite a few people who like riding bikes. And so if you look across those systems, there's been a lot more than 100 million rides since 2010. If you look at Citi Bike, which is the bike sharing program in New York City itself, these days it's over 950 different stations, something like 28,000 docks. That's estimated. It's not, I'm not sure what the exact number is, but I do know that the number of bikes is something like 14,000. And the fact that the number of docks is twice the number of bikes is not really an accident, right? There's a pretty good reason for that. Something like 180,000 subscribers for the Citi Bike system. Because Citi Bike operates in two modes. You have subscribers who have an annual pass, and then you have folks who are kind of like tourists in New York who just want to borrow a bike for a day. So we have those two kinds of users, but the dominant users are these subscribers. Last year, they had something like 21 million rides, and at least as of about a month ago when I was just updating this statistic, the record day had been September 21st in 2019 with about 100,000 rides. So it's a big system. There's a lot going on here. So I want to show you, give you a sense of what a typical day looks like in the city. And here I'm showing a map of Manhattan. And each dot that you see there, or each circle, corresponds to one of the stations. And I'm not only showing a very small fraction of the stations here because we prepared this video a very long time ago before the system expanded considerably from what you see here. But this was the picture of it as of a few years ago. And what I'm going to do is I'm going to play a typical day. So you'll see time advance up at the top of the screen. I'll just switch to a laser pointer so you can see what I'm talking about here. So I'm looking at time up here at 12 a.m. And so I'm sitting here at midnight, and now I'm going to get the game running, and we're going to start watching a typical day in the life of the bike sharing system. So actually, it looks like I need to have a pointer before I can do that. So let me try this and see what happens. Okay, it's advancing now. It's a bit hard to see that there's anything going on. You may not be able to tell that there's any change, but that's because we're in the middle of the night right now. There's just no biking activity going on. So, but we're about to hit the morning rush, and you can start to see the transport centers lighting up. Those bright red blobs are train stations and Grand Central and locations like that. You also see down the bottom right, a big red area there. That's called the East Village. That was a whole bunch of people waking up, getting on bikes and going into the financial districts, the Midtown area, to work their day. And now we've reached the middle of the day. Things are sort of pretty steady. We're not seeing too much change. And but as time progresses, we're going to move into the evening peak. And all those flows we saw in the morning are going to be reversed. All those people in Midtown are going back home to the East Village and to their other places where they live. All of the colors have swapped. So where we previously had bikes disappearing at a great rate, now they're arriving at a great rate. And these kind of tidal flows of commuters make this problem super hard. What's the problem? Try to minimize the number of times when people can't find a bike or can't find a dog. So if you dig in a little bit and you look at some of these stations, you can track, because Citi Bike has just fabulous data. You can track the number of bikes that are present in a station over time. And so here we're looking at 3 different days at the same station, which is at 52nd Street and 5th Ave. And you see on the horizontal axis is the time of the day. It's a 24-hour clock, starting at 6 a.m. actually. And then on the vertical axis, you see the number of bikes in the station. And if you just look at this, this left-hand image for a second, so what you see is this kind of giant increase in bikes. So what's happening is bikes are pouring into this location from somewhere. And then what's going to happen is those commuters are going to head off somewhere else. There are some pretty wild fluctuations here because there's also people picking up bikes. So the numbers are not just monotone increasing, they're also fluctuating a bit. But then you see these giant drops. You can probably see these sort of vertical cliffs. And these are, what's going on here is this is rebalancing. So this is the Citi Bike people running around thinking we've got to clear space in the racks for people to return bikes. And as fast as they can remove those bikes from those racks are filling back up again. And you see similar patterns across the weekdays here that are depicted. And you see that opposite kind of rebalancing in the afternoon. In the evening peak, you see these incredible climbing, sort of these cliffs where you're going up, right? And this is where Citi Bike folks are dumping bikes into this location. And then there's this giant sucking sound as those bikes are just ripped out of there as fast as they can put them in. So you can see how they're just being really soaked up. And it's even as late as 9 p.m. in this location. So you see similar patterns on similar days. So that's good news. That tells us there's some predictability to this behavior. If we dig in on one particular station, there is a difference, a substantial difference between weekdays and weekends. So here you're seeing 3 weekdays and then 2 weekends. And so we have to take that kind of stuff into account, and we do. You can also see some kind of fun stuff. This is probably not so important for the analysis, but this is just kind of interesting, I thought. So here on the horizontal axis, I'm plotting the distance that people are going to travel on one of their bike rides from one station to another. And I'm plotting that on a log scale, and that's why it goes negative. And then on the vertical axis, I'm plotting the log of the number of seconds of their bike ride. So duration on the vertical axis, distance on the horizontal axis. And I'm not going to go for speed. I'm not really interested in that right here for this particular conversation, which maybe you were thinking I was going for. What I want you to notice is just, do you see that kind of there's kind of a level plateau here at about 8, which is, this is the log of the duration in seconds is 8. If you translate that into minutes, that's about 45 minutes. If you look at 45 minutes and why is that significant? It's because if you take a bike for more than 45 minutes, you have to start paying for the extra time you had it beyond 45 minutes, beyond your subscription. So what do? We all do the same thing. We're all cheap as anything. We ride until we get close to 45 minutes. We park the bike that we're riding into one of those docks, reset the clock, maybe even grab the same bike, grab a different bike, whatever, and head off again. And that's what we're seeing. That's why there's this kind of weird plateau, we think, at 8. That's kind of a fun thing. It's not that important for the analysis, but I don't know, it's just kind of fun to see this stuff showing up in data. So we use statistical methods in this data to infer the things we need. And what do we need? We need to know the demand for bikes. So how many people want to pick up a bike at a particular station at a particular time of the day and for a particular day of the week. And the way that we do that is we look at each station, and for each half-hour interval, let's say Mondays from 8 to 8:30 in the morning, we'll estimate how many bikes are being demanded at that time by saying, in our data, how many bikes were picked up in that half-hour period. Maybe that half-hour period is replicated over many weeks, so we'll count that up over all of those weeks. And then what we do is we just divide by how much time we've been watching things. And so if let's just to make things a little bit simpler, let's say that we had 100 bikes picked up over 1 hour's worth, so 2 weeks, 2 1.5-hour periods, 1 in each week, right? So I don't even remember what I said now. Let's say it's 100 bikes over those two half-hour periods, so that's 100 bikes an hour. That's not what we estimate the demand to be, because if we run out of bikes for some part of that those 2 30-minute periods, then effectively we've choked off our data. We don't have any information about people trying to pick up bikes when there are no bikes available. So what we do is we reduce the denominator here. The denominator here is reduced to the number of minutes when bikes were actually available in that station. And what that's doing by reducing the denominator, we're increasing the fraction. And so that's elevating our estimate of the nominal demand for bikes. So that's the natural thing to do here. And that turns out to make a big difference. I won't go into the details, but that does make a big difference. We also need to know where bikers are going. And this is actually pretty straightforward. So you look at where they picked up their bike, you look at where they're dropping off their bike, and we can infer that. There is, again, some kind of censoring, like I was just describing, because if somebody tries to return their bike and there are no docks, one option is for them to go to a nearby station. We don't want them to do that. We'd like them to be able to go where they want to go, but that happens as well. And then finally, we can estimate the biking times. That's very straightforward as well. So we want to know all kinds of other stuff as well, and there are some things that we just will never know. So what do riders do when there are no bikes, apart from texting us and telling us that we're doing a rubbish job with our rebalancing? And what do riders do when they try to return their bike and there are no docks? So we have some idea of some things that they do, but we're not that sophisticated on that front. We're going to try to avoid these situations, though, with all of the modeling that we do. So the goal is to avoid this sort of thing happening in the first place. So maybe it's not as important to understand. And that brings me to the modeling and the optimization that we do to try to reconfigure the system so that it's a better experience for everyone. So we've done all that statistic stuff. Now we know something about the system. Now, how do we do this optimization stuff? And maybe you've taken an optimization course. If you have, you might have had the following recipe hammered into your brain. This is something that I'm teaching right now to my students at Cornell Tech in New York City. So you have, whenever you're facing a decision problem, you define your decision variables. What can you control? What are you trying to decide? You have to choose your objective function. What is the thing that you're trying to maximize or minimize? And then you have to define your constraints. These are the things that limit you from just having the world's greatest system. There's always something that gets in the way, and that's the constraints, right? So what are our decisions? Well, like many people who got into this business, we were thinking the central question is, how do you move the bikes around through the city overnight so as to ensure that the system is set up really well in the morning so that those commuters can get the rides that they want. So how do we move bikes overnight between the stations so as to ensure that the starting configuration for the next day is really good? And there's a bit of a story here, so I'll just put that little pointer out there. Then we have our objective function, which is to minimize unhappy bikers. And the definition of unhappy bikers is somebody who encounters an outage, either can't find a bike or can't find a dock when they want to return their bike. And then the constraints we're looking for are, well, there's all kinds, but the primary ones are physical constraints. Those stations have capacities. They only have a certain number of docks or racks, same thing. So they only have a certain number of those. And there's also physical constraints on how many bikes we can move overnight, but we're going to ignore that for now and just say, what's the right configuration in the morning that we should be aiming for? And then we can use that to inform the trucks as they drive through the night to move bikes. So in a bit more detail, let's drill in. So let's define my decision variables. So I've got B1, that's a decision variable. It's the number of bikes I'm going to position at station 1 at 6 a.m. And remember, I'm pretending that I can just magically get those bikes there. B2, same thing at station 2, all the way up to B950. So I'm trying to choose these 950 numbers, which represent the inventory of bikes at those stations in the morning. And I'm going to let little c of b, where b here is now a vector, so I'm indicating it in bold. C of b is the expected number of unhappy bikers. So this is the people who can't get a bike or a dock. And that's measured over the entire course of the day, not just early in the morning, but across the entire day as a function of this vector, capital B. So we want to minimize unhappy bikers, C of B, over all choices of this initial inventory B that satisfy our station capacity constraints. And then that all sounds fine, and that's actually not that hard to write down like that. But the key question is, how do I compute this function little c of b? So how do I compute the expected number of unhappy bikers? So here is a principle that I want to espouse when one is doing this kind of applied modeling. I think it's really important to start with a very, very simple model and get an answer to that very, very simple model. And that answer may be horrible in terms of the overall thrust of what you're trying to achieve, but you've got an answer. And now you can move to a more sophisticated model that maybe gives you a better answer. And that more sophisticated model is going to be more complex than the previous one, so it might take a little bit more time. And you should probably, at least in my view, work on a kind of an exponential scale here. So model 0 should be something you can just about write down straight away, and I just have. Let's start each station half full. And in fact, this is what Citi Bike wanted to do when we first started working with them. And we, very quickly moved away from this idea. But this is what they wanted to do at first. Now, it's not a very good answer because of those tidal flows of riders that we were looking at before. But it's an answer. And then we can say, well, can we improve that, right? And so that's where I want to go next. So we're going to move to an improved idea. What we might do, maybe you've thought about this, maybe you can sort of simulate this thing. We could replay all the rides that we see in our data over a day, starting from some proposed allocation of bikes to all of those stations. So we could essentially simulate this thing. And then we can just record what were the number of outages that resulted when we started with that particular value of B, that vector that we're trying to choose. And then you can just play with that vector B and look for a good solution. And here, when I wave my hands and say, play with that vector B, I'm really talking about running optimization algorithms. But again, I'm going to skip some of that complexity and just move on. And this approach is actually not too bad, but it has two pretty serious weaknesses. The first weakness is that we already talked about censoring. So the ride data doesn't register a ride when you run out of bikes, and it doesn't register a return of a bike when you run out of docks. So there's a problem here in just replaying the rides that we've got in the data. We're missing a lot of the potential demand that we actually should be trying to serve. The second weakness is there's a lot of these potential vectors of allocations of bikes to stations. And how many? Well, suppose that each station has 10, something like 10 docks. Then you've got 10 options, actually 11, but let's just pretend it's 10, you've got 10 options for how many bikes to position at that station in the start of the morning. So with 950 stations, 10 times 10 times 10, 950 times, gives you this 10 to the power of 950. Now it's a little bit smaller than this because we've got a limit on the total number of bikes we've got to play with. Moreover, there are other complexities, like the station capacities vary all over the place. We've already seen a station that has capacity of 40, not 10. Anyway, the point is there's a lot of these B vectors. And so we can't just do some sort of exhaustive search. We've got to do something a little bit smarter than just play with B. So a second approach you might adopt that will help us a little bit. Let's use statistics to fit arrival rates of bikers to each station, and we've already seen ways of doing that. And then what we might do, once we've got those flow rates, which are things like 5 bikers per half hour want to pick up bikes from the station, and 10 people want to return bikes to the station. With 5 bikes being sent away, 10 coming in, we've got a net flow of 5, right? So we can trace those flows. That's what I mean by this, and I'm going to show you that in a few moments. This idea of using statistics solves that first weakness that we mentioned before, weakness 1, that the ride data doesn't register ride. So that's good news. We still need to deal with this problem that we've just got this incredible number of potential configurations that we could start with. So if we just trace those flows, let's just see how that works. So on this plot, I'm showing you 6 a.m. through to just something like 7:30 or so on the bottom. And then on the vertical axis, I'm showing you the number of bikes that we see at a particular station. And this tracing of flows looks something like the following. I have an initial inventory of bikes, and I watch that over time, and I see it growing. And it's going to keep growing because I've got bikes pouring in net to the station until I reach the station capacity. And then it's just going to sort of stay flat at that capacity because we can't fit any more bikes in. And then maybe the flows reverse. And we do see big reversals in flow rates, particularly at times of, say, shift changes at hospitals. So then we see something like this curve starts to descend. And then maybe the rate changes a little bit more in the next half hour, and it starts to descend even more. And then we bang into another boundary, and now we're sort of stuck at that boundary as well. And what we care about are these boundaries at the top and at the bottom. And so you can see that if I were to have lifted this whole curve up a little bit from at the start, if I had lifted the whole curve up, I would be spending more time banging into the top boundary and less time banging into the bottom boundary. And so we can count that time that we spend banging into boundaries and trade those off. So if we start with too many bikes, we hit the upper boundary a lot. If we start with too few bikes, we hit the lower boundary a lot. So probably there's going to be some kind of sweet spot here. And that suggests that optimization could work. And in fact, the more precise way to say this observation is that the objective function we're optimizing is convex. And if you've encountered convexity before, good for you, then you know what I'm talking about. We're trying to minimize something, that thing that we're minimizing is convex, so we're going to be in good shape for optimization. If you don't know what that means, just imagine that the function looks a little bit like a bowl. Unfortunately, it's a 950 dimensional bowl, so it's a bit hard to visualize. I haven't got a hope. Being an engineer, I don't even claim that I have any sense of what this looks like, but it's bowl-shaped. And that means that if we run optimization and we just keep looking for a better and better choice of ways to allocate this vector B, we're eventually going to be able to solve this problem to the optimal solution. So that's really good news. Love that. Okay. But there is a serious weakness with the way that I've described this to you so far. This is assuming deterministic flows. So it's assuming that I actually know exactly how those flows are moving, that those lines that I was showing you had a certain slope that I was pretending I knew, and there was no fluctuations like there is in the plots that we saw earlier. And that is a problem because imagine you have a station that has perfectly balanced inflow and outflow. So the net flow is 0, right? So if the net flow is 0, then you would just see a horizontal line. It'd just be a flat line for the inventory. And therefore it doesn't really matter how many bikes you allocate to that station, you're all good in this deterministic way of thinking. So we already saw a theorem up above that was supposed to help us out with this. Here's a much better theorem. I'm much more proud of this second theorem. This second theorem says this function is actually still bowl-shaped, even if you make fairly realistic assumptions about how those flows change. So it's maybe not so surprising that this holds true given what we've already seen, but it's nevertheless a bit of a tough ask. And in fact, I am hiding a PhD thesis in that statement. So one of those people that I didn't really go into the details of on the first slide did a combination of, if you know what this stuff is, continuous time Markov chain modeling, essentially queuing theory, but not in steady state kind of methods. So using transient performance measures, because the transient behavior here is super important. And then we also use coupling theory to try to prove this result. So if you know what those things are, then you've got some insight as to what we were doing. If you don't know what those things are, doesn't matter, because we've got some cool pictures coming up. So let's take a look at some results of what happens here. So here is a picture of one station, and I'm plotting this objective function at that station. So as I vary the number of bikes that I position at that station at 6 a.m., you see the expected number of annoyed people on the vertical axis. And you see that if I have no bikes there, a lot of people are annoyed. And if I have a lot of bikes there, fewer people are annoyed. And so this is clearly one of those stations where it's important to have a lot of bikes. So it's one of those stations where people are demanding bikes. There are other stations where you see something about much more complicated. It's bad to have too few bikes, but it's also bad to have too many bikes. And this is a situation where there are people both dropping off bikes and picking up bikes. So it's one of these stations that somehow has somewhat balanced flows. And then there's that nice sweet spot in the middle. And then we can do this for a whole bunch of different stations, and you see these different curves. And so all of these curves that you see, it's super important that they look like bowls or are straight lines. And that is telling us that we can solve the optimization problems efficiently. So let's take a look at let's wrap this up now, and let's look at the massive impact we've been able to make by moving bikes around through the system with these methods. So what I'm showing you is a map of New York as the situation looked at midnight on one night. And what we've done is we've got a circle for every bike station here, and I'm coloring that station white if things are good, right? So if that station has the right number of bikes at midnight for the usage that we predict starting at 6 a.m., I'm going to color it white. If it's got the wrong kind of number of bikes, and not just off by one or two, but off by a lot, I'm going to color it red, with darker red being worse and worse. And then I'm coloring neighborhoods as to how well balanced they are relative to the demand. So where you see these red blotchy neighborhoods, this is really bad news, and we want to fix that. And now what I want to show you is what happens after we run our algorithms. We use our algorithms to figure out a good target for the morning, and then we run an overnight rebalancing operation where trucks are driving all around the place, moving bikes in and out. And I want you to see the dramatic change in this picture at 6 a.m. So here we go. There's the picture for 6 a.m. Now, if you are paying attention, you are thinking at this point, what's he on about? Those pictures look basically identical to me. And I would say, yeah, but no, not quite. No, look at this. Look, I'm going to show you. There's a difference. You can tell. Each of these green arrows points out a difference in the model. Now, what am I on about, right? The point I want to make is we are not achieving what we want to achieve. We're not moving nearly enough bikes overnight. It's just physically impossible, given the number of trucks that they can afford to run, to move bikes around this system overnight. And so we're not moving nearly enough bikes. Now, this indicates, the reason I bring this up is that I want to point out something that's quite important. When I'm working, or when we as folks who are interested in this kind of thing are working with companies or working with organizations, we get a substantial benefit. We discover the kinds of problems that are actually important to solve relative to the ones that people think are important to solve. This is a setting where most of the bike sharing literature that's out there is actually dealing with this problem of how to do the bike pickups and drop-offs through the system so as to achieve a target inventory for the morning. And these bike sharing companies of scale really can't afford to do that. That's the wrong problem. So it was super fortunate for us that we were working with Citi Bike, so we could learn this, and then we could change direction. And so that's what we're going to do here. So we're going to say, well, we can't move bikes nearly quickly enough, but is there still something we can do to improve the user experience? And there is. We could move docks. So what we could do here is we could say, we'll drive a truck around Manhattan and we will pick up some of these docks. They're heavy, but we'll pick some of them up. They're just freestanding and sitting on the pavement, but they're heavy. So we'll pick them up and we'll move them once, right? And we'll do that maybe once a year or something like that. But then each morning we'll also have overnight moved bikes as well. So I want you to think about this as actually being a two-dimensional optimization. We can move docks and we can move bikes. And so you have a two-dimensional optimization. There's 2 dimensions for every station, and we have 950 stations, so it's about 2,000 dimensional optimization problem. So again, we need to use structure in the objective function, and all I'm going to say is that we're using a lot of multi-modularity theory, which is related to convexity that we were talking about earlier, and so that means somebody else gets a PhD, life is good, and we get to think about these fun problems, and we get to have some impact. So when we do that, when we solve those problems, and I'm just skipping completely over them, I apologize for that because I want to get to the kind of the cool results, we get pictures that look like this. So this is a map where I'm showing you if we were to do the optimal thing and just grab docks from somewhere and put them somewhere else, and I give you a limit of a certain number of docks you can move, what happens is you get a map like this. In this picture, we're pinching all the docks from Brooklyn and we're moving them into the East Village. That blue area is where we're dropping them off. So this is the optimal thing to do mathematically. Politically, this would create a firestorm because the mayor of Brooklyn would scream at us. So we can't do this. And I'm not kidding, they actually would yell at us. This is it's a venture that's a mix of public and private. City Bike is a private company, but they get the real estate for the stations for free from the city. So the city has a lot of say in what they do. If we were to say, well, let's increase the budget just for now and say, can we move even more docks? Then you sort of see the same kind of patterns. And if we move even more docks, it's the same kind of thing, but maybe it's a bit more complex. So we can do calculations like this, which guide the way that docks are moved around the city, and docks have been moved around the city according to our directions. Which brings me to a few interventions that we can take to try to make this system work better. And all of these interventions are built on the ideas that we were talking about earlier. So maybe a clever calculation, or at least I claim it's clever. It's I've got to blow my own trumpet at some point. A calculation of the expected number of unhappy bikers as a function of this initial inventory, not just of bikes though, but now also of docks. And then the structure that you try to identify in there using this concept of multi-modularity to render the problems solvable. So here's a picture of a guy who actually does work, or did work, on the overnight movement. This is a box truck. A box truck can hold about 50 bikes. They also have sprinter trucks, which can hold about 20. And they do this rebalancing overnight from 11 p.m. to 6 a.m. when things are pretty quiet in the system. So they sort of drive around and do what they can. So we solve a bunch of integer programming optimization problems to show these folks or help guide these folks in the schedules, the routes that they're going to drive, and how many bikes they should pick up and drop off. This is one intervention that we have done. This is the one that probably most of us are thinking about when we think about bike sharing, but there are actually quite a few others. Here's another picture. You can see a guy in an orange jacket there in the photo on the left. He's a guy who works for City Bike, who moves bikes around. And you see that kind of crazy looking trike he's riding. That's actually quite a small one. That's probably got a capacity of about 6 bikes. But you can get trailers that hold, actually the 12 here is out of date. You can get trikes that hold up to 18 bikes. And these guys ride around during the rush hours in Manhattan, because in Manhattan you can't get trucks through the city. It's just too slow. So these guys somehow manage to get through. I think they ride on footpaths and do all kinds of crazy stuff. And what they do is, rather than moving bikes a really long distance, which is really infeasible given that they're doing hard physical work here, we look for station pairs that are close to one another and have opposite usage. So there's a surplus of bikes at one, a shortage of bikes at the other, and they're not too far apart. And then the goal here is to identify station pairs where these trikes can be effective. This turns out to be a able to be, you can formulate this as a problem called a matching problem, which is a combinatorial optimization problem. It involves identifying those station pairs. Solving the matching problem itself is super easy, it's super fast, but computing the value of a pairing is very difficult. So in the right-hand side, you see a bunch of pairings of stations. Those are actually the optimal solution for one particular instance that we've tackled. Computing the inputs to, how valuable is a particular pair that you see there, that's the hard part. And that uses many of the techniques that I alluded to earlier. Here's another shot. This is for corral placement. So this is where life is just so crazy. You've got bikes pouring in and you've got no docks to put them anywhere. So what City Bike cleverly did was they said, well, let's create this thing called a corral. And this is where one of their employees is standing at the station and has corralled off the area. And then people return their bikes at some crazy rate into that location. And all this person does, this valet, all they do is they just sort of stack the bikes. And the bikes are not locked up. You can see them all just sort of lined up here. So you do need somebody there to keep an eye on them because New York is not known for its honest people. And so we have this kind of situation. Now the optimization question is where to put these corrals. And those corrals can help an entire neighborhood. And so when you look in the right-hand panel of the screen, you see all those circles. And those circles are showing you where this is valuable. So again, we solve an optimization problem and that's useful. But this is my favorite one. So this is our favorite intervention. This is called Bike Angels. It's an incentive scheme that Cornell proposed to City Bike, and City Bike took a while to go for it, but they eventually went for it. And I want to just give you a sense. It's kind of like a frequent flyer program. When you take a ride that is a good ride, that picks up a bike from where we don't want bikes and drops off a bike where we do want bikes, you get lots of points. So here's Hans, a quote from Hans. I don't know who Hans is, apart from his name is Hans, and he lives in Midtown. I like to do a Bike Angels workout where I'll bike north in Central Park to an empty station, then run back down the park and repeat a few times. Love this guy. What a wonderful guy to have on the team, right? So he's rebalancing the system for us, and he's accumulating these points. So you might be worried that we're spending a lot of money to have Hans helping us out, or Kelly help us out. And both Hans and Kelly are looking at a real-time map on the right-hand side that you see in the bottom right, which is showing you the point values of the different stations. And those point values are coming from the optimization calculations that we talked about before. I won't go into the details, but I just want to show you something interesting here. What are they earning for their work? You see these pins and steel keys and plastic keys. This, I hate to say the word, but this feels a little bit like trinkets to me. But actually, people are getting better rewards than that. They are actually getting non-trivial rewards, things like discounts. But one other thing I want to show you, do you see this leaderboard on the left-hand side? I want to mention something about the power of gamification. So what we did here is I didn't realize this was going to happen, but this happened. City Bike said, let's post the top point getters over a month. And if you're thinking about this, the scale of the points that you can earn correctly, you should be thinking about something like 250 points earned in a month for somebody who worked every day and had the perfect commute morning and evening over that month. So working 30 days in the month, no slackers in New York, and earning lots and lots of points, they would get about 250. And you can see the top point getter here earned something like 2,400, so 10 times that. But actually it turns out that CC324 is a bit of an amateur. Here is somebody called Joe, who happens to be the second place getter in this table. This is Joe's month this is one instance of Joe's month. So he's just blown by 2,000, right? That was nothing. He's still going. He's earning these high value points across the year. And you sort of think, well, is this guy human? And he just kept going. And he got to nearly 9,000 points in his 1 month there. So that is just phenomenal. So this power of gamification, this incentive to be the best, has really created interesting behavior in New York City that is just really beneficial to the system. So I guess I'll just move to wrapping this up. This Bike Angels incentive program has really helped in rebalancing, and it's about half the cost of the other methods that we have available to us. The cost comes from the rewards that folks receive. It's been implemented all over the place, certainly throughout the Motivate system in the US. It's actually spread beyond there as well. So one important consideration here is the way that you might think about rewards. It turns out we're all a bit risk-seeking at low levels of reward. So if you look at these two options here in this last bullet of a reward that you might receive, and I've just made up these numbers, but they're a good example, but they're not realistic. So would you rather have 10 cents per ride that you do for good rides, or would you rather have a 1 in 1,000 chance of winning $100? And I know which one I prefer, which is the $100, right? And so I'm actually risk seeking at this low level. And in fact, I'm in the majority. Most people would rather have the 0.1% chance. That actually, these two things are the same price to Citi Bike, but the one on the right, the 0.1% chance of winning $100, induces much stronger behavior in users. So that's the one that they use. So the system's been implemented all over the place, even spread to Montreal. So it's all over the Motivate system. So I want to wrap up by just saying this bike sharing world is data and optimization driven, certainly for Motivate across the entire US and in many companies worldwide. If you're solving these optimization problems, think about your decisions, your objective, and your constraints. I think it's important when doing this kind of mathematical modeling that you build a succession of models. Don't try to jump to the ultimate model, but build a succession, and you can stop when you feel like you've got enough complexity. I call this actually the drop dead philosophy, because if you drop dead tomorrow, you've got an answer for your client. Bit cold, but there you are. Rather than focusing on rebalancing, which is what we thought we were doing, moving the bikes around, we should break the rules. This is the Cornell engineering motto, break the rules. So we're going to change the question, and we're going to ensure that we get some impact there. The incentives just blew my mind. I did not predict that that would have as much impact as it did. And finally, I guess, if you have the opportunity, try to work with an awesome company like Motivate and Citi Bike are. They're a wonderful group of people to work with. With that, I'll stop and maybe ask if Matt wants to rejoin us.
Hi there, Shane. Thank you very much for a great talk. So we now have an opportunity for a Q&A session. There's a couple of questions posted, but I think you've already answered one of them really well. The first question was, would financial incentive schemes work for members who volunteer to ride bikes from full to empty stations? And I think you've really pointed out that works really well. The second question that's up there at the moment, and I'd encourage everyone to post their questions even now, but the second question is, have you assessed if there would be any change in the degree of angriness if you move from a bike share model which is using physical docking stations to one that was dockless?
Yeah, so that's both of those questions are great. It's terrific that somebody recognized the value of incentive schemes up front. I had not believed or not expected that would have the impact it would. For the second question of moving to dockless, I'm not a fan of dockless systems in general for a city the size of New York, because the chaos around Grand Central Station or the Port Authority bus terminal in those rush periods would be just off the scale if it was a purely dockless system. Having said that, I do see the value in having dockless systems when you move into the sort of quieter regions. So I'm actually quite a fan of the notion of having a kind of a hybrid system where you have docked stations in the sort of core areas of the city, and then maybe dockless in the outskirts. I've not studied those models at all, but I do recognize that they have, I think, quite a bit of potential. The way that we're taking our work now is through e-bikes and thinking about electrifying the fleet.
So I'm interested in at what scale you think the situation changes. You may know Adelaide has a dockless scooter system being trialled. And I wonder if you said Melbourne, it's not very suitable. What do you think about Adelaide?
Yeah, I have been to Adelaide. Yeah, I have met, but that was before I'd actually met you. So that was a bit of a shame. But yeah, I'd been there, and I just love the city. It's a beautiful place. And I think it probably is at a level where it's probably not too intrusive having these scooters. Nevertheless, there will still be some places where it's frustrating. And so there you probably want to have some kind of regulation. Whereas, as you've sort of rightly pointed out, if you're in the middle of Melbourne, it's really a non-starter. You do have to have some kind of organization.
Okay.
Yeah.
So there's a little bit more feedback from a couple of people's, just a general thank you. There's also a comment that Dockless ends up in the Yarra, which is a river in Melbourne.
Yeah, we've seen a little bit of that too, swimming bikes, yeah.
Yeah, there's been a bit of that happen in Adelaide, I think you.
It's probably by design, those are probably amphibious bikes that just...
Amphibious bikes. There's a very long question from Angela, so I'll do my best to relate this one. Starts out by saying, love the work, particularly as a rider. There's not a gamification system here, though, in Brisbane. There's a comment that our docks may not be movable. I have no idea. Adelaide, as I said, doesn't really use the dock. Other challenges are system errors, docks said to be full but isn't actually, a bike returned but not registered, bikes said to be available at docks. Do you have all of these sorts of problems?
Oh, no, this is wonderful. Angela, thank you for, clearly you're a power user of this system, so that's really great. I mean, you're touching on a lot of great topics. So the issue of non-movable docks, that does come up. So when they do something brilliant, like concrete the little guys into the ground, they're not very movable. And there you probably just use these techniques for thinking about system expansion and not actually moving docks, which is also sort of system contraction locally. So you can use these kinds of techniques for thinking about expansion, but not necessarily contraction when people have non-movable docks. The other thing you mentioned about bike maintenance and issues with bikes showing up but not being usable, or the opposite, that does happen. One of the more amusing ones was where a bike just didn't seem to be getting used, and we eventually found out that a bird had left a deposit on the seat. So there's stuff like that. There are also other situations where you try to check the bike out and you really can't, because there's something faulty with the key mechanism. And so that does show up in our data in various ways, but it's very hard to interpret some of these things. So there are these other dimensions that you're bringing up, which we've encountered along the way. And then we've had to figure out which ones we can safely ignore and which ones we do have to actually model to get something that works for City Bike. So that's where the art form, I think, comes in a little bit.
So I've got another comment about Melbourne's system saying that Melbourne's dockless system was a failure. So that perhaps adds to your, your comment. There's a question about whether tourism makes up a significant proportion of rides, or whether there's seasonal changes in tourism numbers.
Yeah, so the tourism is actually not that big of a fraction overall. It's still non-appreciable. It's still appreciable, sorry, but it's not a big part. It's mostly commuters. But if you look at Central Park, there's an enormous amount of traffic that goes around Central Park, where people pick up bikes and then drop off bikes somewhere else as they're rotating around there. So there is that. New York is also a city that has tremendous differences between summer and winter, and so you do see these massive seasonal changes across the year. So we have to adjust our plans as things progress.
So that leads into another question, which is, did you have to build different optimization models for different days of the week, weekends versus weekdays, and I guess between different seasons as well?
Yeah, it's absolutely the case. So different plans for weekdays versus weekends. I can't remember if we distinguish between Mondays and Tuesdays or Thursdays and Fridays, because sometimes there are differences on the ends of the week, but I don't remember about those. Certainly for the weekend, yeah, totally different.
So just checking through a long list of questions. So I've got one question here, which is, do you know if similar optimization techniques are employed when bike sharing services are being implemented in a city, say for the placement of docks, or is the prediction of flow a different problem altogether?
Yeah, I mean, that's a good one, right? So we were asked at various times to predict system expansion questions for Motivate, this company, in other cities that we'd never considered. And one of the things we thought about was taking our models for New York and transplanting them across to San Francisco. That was where they were planning on expanding. And we were thinking about that, and then we realized that would be a really bad idea. You know, New York is pretty flat, and San Francisco is, let's just say, not. So it's a very different environment. So what we ended up doing was doing a kind of a regression analysis. So we grabbed a whole bunch of data from, I'm sorry to say it, but Wikipedia on bike sharing programs across the world, and got some sort of data about each city. So how hilly is it? How long is the riding season over the course of the year? Those kinds of things. And then we just did a prediction of, using those predictors, what would be the bike volume. And then we used the same kind of prediction for San Francisco. So we did something like that. And it ended up, we were pretty close to City Bike's internal predictions for what was going on there. So we were pretty happy with that. But we couldn't, your implicit question is correct. We couldn't just take this model and translate it across.
Okay, I think we're just about out of time there. And I can see there's still a few questions that I haven't managed to get to, and I certainly have a bunch of questions of my own that I would love to ask about this work. I think it's really, really fascinating. I just want to thank you again for being willing to participate in this virtual lecture series. Just a reminder for everyone participating and anyone else is that this series of lectures is being recorded, and it will be available on the ACEMS webpage. Thank you once more, and I'll finish things off there.
Okay, well, thanks very much, everybody, for coming, taking a bit of your day to be here. One last thought, these programs are actually quite profitable, and their ridership has gone up during COVID-19 because people are staying away from shared rides and taxis. That's good news.
Okay, let's leave it there.